We consider repeated strategic interactions or games in computer systems, with applications including internet routing and advertising auctions. A standard behavioral assumption in these settings is that players act using regret minimizing strategies to decide their actions. Here, regret is simply defined as the difference between the losses incurred by the player's actions and the best action in hindsight. It is well known that when all players achieve small regret, their social cost, which is the measure of performance in this setting, will be approximately optimal. In this paper, we look at what happens when players use algorithms with low approximate regret, which is a simple relaxation of the usual regret. We show that players with low approximate regret achieve fast convergence to efficient outcomes, and they do so with less feedback in a broader range of settings than in previous work. Let's talk about how the efficiency results for regret differ from those of low approximate regret. When all players use regret minimizing strategies, they converge to a social cost that's rho approximately optimal, with an extra additive term determined by the regret bounds of the individual players. For typical algorithms and analysis techniques, this sum of regrets decreases at a rate of 1 over root t, where t is the length of the game. When all players use algorithms with low approximate regret, they converge to a social cost that's within a factor rho plus epsilon times the optimum, but their additive term is now determined by the sum of the approximate regrets. The good news is that this approximate regret term goes down at a rate of 1 over t. This is what is typically called a fast convergence result.
Previous work also achieves fast convergence to efficient outcomes, but requires players to use specialized algorithms and have access to expectation feedback. Our work improves in multiple domains. First, we only require players to have access to realized feedback. That means that they only observe the loss of their actions given the actions selected by the other players. Instead, previous work needs access to expected losses, which has information and computational issues. Second, our low approximate regret property is ubiquitous and is satisfied by a broad range of simple algorithms, such as hedge. This is important, as learning is, in our setting, a behavioral assumption, and the results are only predictive if they allow players to select algorithms from a broad class. In contrast, the guarantees of previous work require the players to use specialized algorithms. Our results also extend to bandit feedback settings, for which we provide a new algorithm. Last, our techniques are useful in settings where the player set evolves over time. There, we broaden the class of learning algorithms that achieve good efficiency in dynamic population games with high turnover. For this, we use a shifting extension of the low approximate regret property. If you want to hear more about this work, come by our poster on Wednesday at poster 157.